We're continuing with section 15.4, total differentials. The total differential of a function z equal to f of x, a graph of a function z equal to f of x and y is dz equal to f sub x of x and y dx plus f sub y of x and y dy, and that is partial with respect to x of z times delta x plus partial with respect to y of z times delta y. In these, actually, you see a lot of this in physics and especially in labs, that you find error using the differentials. The total differential can be used to approximate the increment delta z. That's the actual difference between f of a plus delta x and b plus delta y, and f of a and b. Delta x is the difference, z difference between z for at the point a plus delta x and b plus delta y, and z for f at point a and b. And so when is it coming handy? Application of total differentials. Example 8. Use the total differential to estimate the amount of metal in a closed cylindrical can with radius 4 and height 12 centimeter if the sides are 0.04 centimeter thick and the top and the bottom are 0.01 centimeter thick. So here's the cylinder like that. Not the best, but maybe start over. And so the radius over here is 4, but then the outer radius is 4, but then the thickness of the metal is in here is 0.04. So the inner radius is going to be that much less. And then the height. The height is 12, but the lid and the bottom both are 0.01. So the inner height is going to be 11.98, and inner radius is going to be 3.96. And the purpose is to find the volume, the outside volume, and find the inside volume, and subtract and find the actual volume of the metal itself. But that's more complicated to do that with all these decimal digits and everything. So I prefer using the differentials. And so let's say the volume is a function of R and H, because R and H are changing, and that is pi R squared times H. We want to figure out the absolute value of delta V, and delta V can be approximated instead of calculating it like that. Can be approximated by dV. dV we learned from the previous formula. It's partial of V with respect to R times dr, partial of V with respect to H times dH. Again, this is a nice formula for your physics classes also. Now, so I have to find the partial of V with respect to R, evaluate it at the point that is easy to evaluate. Partial of V with respect to H, evaluated at the point that is easy to evaluate. Delta R is going to be negative 0.04. Delta H is going to be negative 0.02, twice of that. But then I have to do the absolute value, so it's just, I'm going to put the positive 1 for both of them and make the entire thing absolute value. And so For r equal to 4, h equal to 12, partial respect to r and h is equal to 2 pi rh, and partial respect to r at 4 and 12 is 96 pi. The partial respect to h of r and h is pi r squared, and then if I plug in 4 and 12, I get 16 pi. Set up the equation, and we get 96 pi times 0.04 plus 16 pi times 0.02. And again, because it's absolute value, I got rid of both negatives. The negative would come out basically. And so it's approximately 4 pi cubic centimeter. It's 13.069 cubic centimeter. Sorry, it's approximately 4.16 pi times cubic centimeter, which is 13.069 approximately. I got here question 15.4. See, 4 positive number, each less than 10, are truncated to the first decimal place and then multiplied together. Use differentials to estimate the maximum possible error in the computed product that might result from truncating. So let's stop the video and think about it and come back. And remember, for example, truncating 3.14159626 to the first decimal place results in 3.1. So what is the function? Function is f of x1, x2, x3, and x4 equal to x1 times x2 times x3 times x4. Now, partial of f with respect to x1 is going to be x2, x3, x4. And partial of f with respect to x2 is going to be x1, x3, x4. And there's a symmetry for the partials. Each partial, if I plug in, what's the maximum value of for each partial? It can be 10 times 10 times 10. So each partial is 1,000. The maximum value of each partial is 1,000. And then remember, so you have to find to approximate by df, you have to multiply each partial by delta of that variable plus another one. And there are 4 of them because 4 variables. Every time each partial is maximum value of it is 1,000, and then the maximum error that can happen by truncating is 0.1. So 4 times 1,000 times 0.1, D is the answer.